This is a crash course on integer partitions, and it's going to be in roughly 3 parts. The first thing is how to build an integer partition. The easy and obvious part, once you built the integer partition, is we'll then get the count for the partition function. And then lastly, I'll give you a little bit of a preview of how you might build a recurrence relation off of these numbers. So let us start off with what an integer partition is. You simply have some integer and you break it up into sums. Okay, so the key thing is the integer, whatever integer it is, can be broken up into a sum. Like for example, 7 can be broken up into 3 plus 4. All integer partitions of a number, there's all the different ways that can happen that are unique. Now here's the key. You always order these sums biggest number to smallest number. That way you don't have to worry about all the ways you can rearrange those individual numbers of the sum. Okay? So if you start with the integer 1, notice the only way you can get a 1 is you can say 1 equals 1. And that's it. That's the only way the sum works, because with integer partitions, you're dealing with your positive numbers. Okay? So what that tells you is if somebody asked you, hey, what is the number of partitions that the number 1 could be written in terms of? Or how many different partitions of the number 1 there is? You'd say, hey, there's just one of them. Okay. Now, we can also do this for the next several integers. Maybe we look at when n equals 2, and notice when n equals 2, we're going to have more choices. You could write your 2 as just plain old 2, but 2 could also be written as 1 plus 2. So this time if somebody asks you, alright, well how many different ways can we partition the number 2, or how many different ways can we write 2 as a sum of other integers, you can say, hey, well there's 2 of them. And again, we assume that we're writing these guys in terms of positive integers. There's one exception to that, but we're going to ignore that exception for right now. So you can keep on doing the exact same thing, but you start seeing a strategy emerge once we get up here to n equals 3 in how we're writing out all the different ways to sum up to whatever your n value is. So with 3, notice I'm going to continue the same pattern that we did before. I'm going to start with, hey, no sum at all, just the number 3. But now I'm going to start being strategic. So next I'm going to say, all right, well, what's one number less than 3? It's 2. Well, if I know that 2 is one of the numbers I want to use in the sum, well, the only way you can get to 3 is 2 plus 1. So right now, a little bit strategic, but not any choices. So then, if you don't use a 2, and you don't use a 3, because we've already looked at all those options, that means your only option in terms of numbers for the sum is all 1s. Okay? So then we can say, hey, well, for 3, if we wanted to break it up into partitions or sum of integers, there's exactly 3 cases, okay? Or 3 situations. Now, n equals 4 is where you start seeing stuff break out a little bit. Because right now you might be thinking to yourself, all right, so far the number of partitions that we had for each integer was exactly the same as the integer. And you might be thinking to yourself, if you're thinking ahead in terms of trying to build a sequence, hey, this looks like a really easy sequence. P of n is going to be exactly n. Nope, I'm sorry, that doesn't work that way. It's way more complicated than that. And 4 is where you start seeing the little bit more complicatedness come out. Okay, so 4, we'll start doing the same strategy that we did with 3. Start off, you could write 4 as just the sum of itself, 4. But you could also say, all right, well, what happens with other numbers? And so strategically, I'm going to do one number less than 4, so 3. 3 plus something should equal 4. Well, there's only one option, 3 plus 1. Alright, so then we look at one number less than 3, and we look at 2, and we say, alright, well, what are some ways that you could add to 2? What are some things you could add to 2 to get a sum of 4? And it turns out, here's where you start getting multiple ways. Always pick the biggest number first, okay? So here in this blank after the plus, we can't use a 3 or a 4 because those are options that have already been taken. These integers have to be written in descending order. That means the only options after this first plus are either 2 or 1. So I'm going to go with 2 because 2 plus 2 is 4. But we didn't have to do 2 plus 2. We could have done 2 plus, well, split up the 2 here. We could have 1 plus 1. Notice at this stage right here, and also it really worked up at 3 as well. In these guys, we essentially reproduce the integer partition of 1, and then down here when we started with a 2, the integer partition of 2. I'm writing this out strategically like that so we don't miss anybody. Okay. Now notice this takes care of all the ways that we could have a 2 in our integer partition. So that means the only thing that we've got left is what happens if we have all 1s. So that would be 5 1s all added together. Not 5, we're looking at 4. 4 1s all added together. So this means that for 4, the total number of ways that we could write 4 as a sum of positive integers is, if we count them up, it looks like we got 5 right there. And notice our pattern broke from the previous 3 guys. Now, if we jump down to n equals 5, we can reproduce this exact same thing, or really not the exact same thing, but we'll do it for n equals 5. So in this case, again, we'll start with 5 at the top. We'll do one number less than 5, which is 4. Well, if it's one number less than 5, we only have the one option of 4 plus 1. Okay? So that was essentially like reproducing the integer partition of 1 after the first plus symbol. Now, that takes care of all the possibilities if you use a 4 or a 5. So next, biggest number in play is a 3. So if we look at 3, we then say, all right, well, to get up to 5, we need 2 more we need 2. So we're essentially going to reproduce the partition from n equals 2. We could have 3 plus 2, or that 2 could have been broken up into 1 plus 1. At this point, we've taken care of all of the cases where we can have a 3 involved, so our biggest number in the sum next is going to be a 2. Now from 2 to 5, what do we need? After the plus, we need a grand total of 3. So we could have 2 plus 3, except no, we can't. That's the same as this guy we already have. Okay, and the biggest number has to be written first. So we're essentially going to reproduce the integer partition of 3, except we don't get to use the 3. We have to start down here at 2. Okay, so biggest number, we put a second 2. That gets us to 4, and we need one more. So we have 2 plus 2 plus 1. Now we also could have had what? This 2 could have broken up into 2 1s, so 2 plus and then 3 1s. And at that point, we've exhausted all the cases where we have what? Where we have a 2 is your biggest number in the sum, which means the only option left down here is if you have all 1s. Okay. So if we count up all of those options, we had what? 1, 2, 3, 4, 5, 6, 7. And this tells you if we're looking at the integer partitions of 5, there's 7 different versions of them. Notice again, the biggest number is always written first. Okay. Now, what if we do one more? If we look at n equals 6, we can do this same exact process. It is going to look a little bit, well, you're going to see it a little bit even more than when we were looking at n equals 4 or n equals 5. So we'll start off and we'll have 6. We could then break it into 5 plus 1. Notice we just broke off. We had started with a biggest number is 1 less than 6. This is the only option, so we then jump down to 4. Well, 4, the difference between 4 and 6 is 2. So this guy, we could put a 2 after the first plus, or we could put a 1 plus 1. And notice this is where we essentially reproduced what? We essentially reproduced the integer partition of 2. Okay. Keep going. The next biggest number would be a 3. And here we say, well, what's the difference? It's 3. Well, we can have the full 3 here. But we also could have, well, how did we break 3 up? 3 could be 3, or 2 plus 1, or 3 1s. So we also down here could have 2 plus 1, and 3 plus then 3 1s. And this is where I'm going to run out of space at the bottom of my paper. Okay. So next, what would be the next thing that we could do? We could look at 4. I lie. Look at 2 is the next number. Okay. Now remember, 2 has got to be the biggest number, so we're only allowed here to add up 2s and 1s. Now the difference between 6 and 2 is 4, so we have to figure out all the ways that we could write 4, but only using 2s and 1s. So if we go back up here and we look at our partition of 4, we're not going to use the top 2 ones because they have numbers bigger than 2 and 1, but we are going to use the bottom 3. So this is now an extra 2 plus 2. We could also have an extra 2 plus 1 plus 1. And lastly, we have 2, and then everybody else is a 1. And at that point, we've all exhausted all the ways that we could use a 2 in our integer partition of 6, which means if 2 used to be the biggest number we can use, now 1 is the biggest number that we can use. And we'll go ahead and write down 6 1s here. 1, 2, 3, almost there. There's the 6th one. Which means if we go ahead and count these up, we can actually figure out how many different ways there are to write 6 as sums of 1 through 6. And in this case, there's 4 over there, 5, 6, 7, 8, 9, 10, 11. Okay? And that gets you how to write your integer partitions. It also gets you what that actual final count is. Now, if you were trying to find some way to write these guys as a sequence formula, first thing is there is no closed form that anybody has found yet. If you're actually able to find a closed form, you would be quite famous because this is something that nobody knows yet. It's still something that people work on. Okay? There are several ways to write this as a recursive relation. One of them duplicates what we were just doing right here, which looks at, all right, what do we do at each stage? It looks like we're pulling previous counts of integer partitions and using that information down here, with the exception that you don't always use all of the pieces. So when you don't use all of the components from your previous integer partition, you would get minuses involved, or you can get minuses involved. Another formula that's very classic that people use is people will count the parts that have how many sums involved. So for example, 5 here has only one number added together. Both the next two have 2 guys added together. The next two have 3 guys added together. Then 4 guys, and then 5 guys added together. And it turns out there's a way to actually write the formula for if you want to partition n, say 5, into 2 pieces. There's a formula for that, and then you do this iteratively from 1 all the way up to 5 pieces, and then add the sum of that all together. This is actually a double recursive sequence because you're doing it in 2 parts, essentially. Okay? But we're not going to go over any of that. Instead, I want to show you something interesting. So if we go back up to our numbers, what I'm about to show you does require one extra thing, and this is forcing an integer partition. It's going back to when n equals 0. So if n equals 0, technically speaking, you could throw it to an integer partition, but it doesn't really hold to what people think of as integer partitions because it's not a positive integer. We're going to force it to make the formula I'm about to show you work here in just a second. So because you can't write 0 as a sum of positive integers, you can only write it with 0 or both negative and positive integers. To make the formulas work in the future, what I'm going to do is I'm going to force it and say, hey, if we tried to write 0 out as an integer partition or as a partition, it doesn't really work. There's nothing there. It's only itself. So this is essentially replicating what would happen if you were talking about the empty set. In other words, it's essentially like there's nothing there. One of the things that these integer partitions can tell you is talking about if you have a set and you want to cut your set up into pieces. The cardinality of the set would represent over here the number, the integer, and then all these different ways are all the different ways that you can cut your big set up into subsets. So like this one here, you didn't cut it up into a subset. This one here, 3 plus 1, would be like you cut your set of 4 elements up into a subset of 3, and then the second set that got formed has only 1 element left into it. Okay? And these would be like counting up those little cardinalities. It's a lot smaller than if we were actually looking at the full power sets of a set, but there is a tie in there. Okay? Now, if we look back at what we were doing here just a little bit ago, suppose we look at, and I'm going to ignore these first 2 guys. Actually, we could probably ignore n equals 2 as well, and that would probably make most of us happy. So I'll come back to n equals 2 if we feel like we need to. Okay. But if you look down here at n equals 3, notice what's going on. It looks like what? It looks like, well, let me actually put a little scratch work here to the side. Okay. It looks like we said, hey, we already know what's going on with 2. We have 2, and then we have 1 plus 2. Well, we want to build up to 3, so what can we do? We can put plus 1 on the end there. And notice that get us to both those bottom 2 guys. Except, well, it didn't fully do what we wanted to. So it's also like saying, all right, we'll go back 1 further and add 2. To what you have, except we already have that one, so I'm going to go ahead and merge this over and get us to 3. Okay. This trick I'm about to show you, sometimes you'll get the exact same numbers, and if that's the case, you're going to need to add those guys all together. So what does this tell you? This actually tells you that, and let me actually do a different color. This tells you that, hey, this first part was a reproduction of when n equals 2. The second part was sort of an adjustment when n equals 1. So this tells us that P of 3 equals the sum of the previous two guys in terms of a count. Okay. Now what happens if we try to reproduce that exact same thing? If we were looking down here at n equals 4, let's see if that same strategy of adding the previous two integer partition numbers together would work. So in this particular case, what if we grabbed n equals 3? So we'd have 3, we had 2 plus 1, we had 1 plus 1 plus 1. Well, let's see if they're actually in here. Well, if we add, well, none of them are exactly in here because they only add up to 3, which means if we add 1 to all of these, double check, do we have them all? Well, yep, we've got this one, we've got this one, and we've got this one. So the only things left are 2 plus 2 and 4. Well, 4 is just everybody all added together, so that one's not going to work really well from a previous term anyway. But 2 plus 2, well, how could we get that? Well, if we looked at the previous guy, 1 back from that would be 2 and then 1 plus 1. Well, this is only the integer partitions of 2, so we only sum up to 2. So to get to 4, we'll add 2 at the end. And notice, what does that do? We now have the missing 2 plus 2, and the only number that's left in the integer partition of 4 is actually 4 itself. So I'm just going to go ahead and add all of those guys together to get 4. Notice, just like previously, this guy is the integer partition of 3, but we added 1 to the end. This one's the integer partition of 2, but we added 2 to the end with a small adjustment at the end. So we could say that the integer partition number, the partition function of 4 is just the sum of the previous two guys. Okay. And this would be awesome and wonderful and amazing if this recursive relation that I just showed you would always work. You just add the previous two numbers together. But unfortunately, the answer is it's not quite that simple. Okay? If it was, it would just be a Fibonacci sequence. So let's see what changes. So suppose we do the same strategy for 5. So what do we have for 5? You want to look at the previous guy, so 4. So we have 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. And all of those are definitely in there if you add an extra 1 to them to bump ourselves up to sum of 5. So that's nice. So I'll go ahead and actually title this. This was our P4 with adding 1 to everything. So then when we look at our next one, we have 3, we have 2 plus 1, and we have 1 plus 1 plus 1. Okay? Now, these guys are the partition of 3, but we want 5, so we're going to have to add 2 to everybody. I'm going to add 2, add 2, add 2. Okay? So let's see what we have already. We've got 4 plus 1, we've got 3 plus 1 plus 1, I'm reading down from here, 2 plus 2 plus 1, 1, 2, and 3 ones, and all 1. So we've got all those guys. New, we've got 3 plus 2. And what did we do previously? Previously said when we had all 1s and we added a 2, we'll just sum those guys all up and get to 5. Bam, we've got that one. And then we notice this guy right here that we have no check mark whatsoever on. It's that thing. Okay. Now, do we have any partition of 5 that corresponds to that guy? And the answer here is, well, a big fat no. So notice if we tried to use the same formula for when n equals 5, we actually have one too many partitions. And there's not a good way to merge it either because there's only 7, make sure there's 7. There's only 7 of these guys, and if you add up all of these different guys, there's actually 8. What that means is this thing is actually already taken care of, and where it's already taken care of, is right there. In other words, duplication. So if you remember inclusion exclusion, where we added things in and then we got rid of the ones that were duplicated, and then maybe we added some more things in if we subtracted, it turns out that one of the formulas, specifically the recursive formula that I'm building here a little bit for you, acts like inclusion exclusion. You'll add a couple previous terms. Every so often it works perfectly as is. Every so often it actually overcounts a little bit, so then you subtract them off. Sometimes that works, and sometimes you have to keep going with your inclusion exclusion. It matters how big your n is. So in our particular case here, we're going to subtract off 1. Now, if we look back at our work previously, we look to see which p of n equals 1. And it turns out there's this one right here, and then there's also this fill-in one that I gave us too. This one that's not really an integer partition, but I pushed it for us because I claimed we were going to need it. Okay? It turns out for this guy to work appropriately, you actually need to go ahead here and subtract off p of 0 is how the official formula would work then. Okay? So this overcounts a little bit, so you add the previous two together, and then you subtract that overcounting a little bit. And then it keeps going. You could do the same thing for n equals, we did 5 right here. We could do the same thing for n equals 6. You can do the same thing for n equals 7. And you add 2 terms, then you subtract as needed. And if the n is big enough, you'd add terms back in again, and then subtract terms back and forth. Okay? But that is the crash course on integer partitions, how to make them, how to find the number, and then a little bit on how to build one of the recursive formulas that tie into integer partitions.